deMorgan's laws are among the most useful tools that we have in doing logical reasoning, and they're a way that we can really extend our understanding of a lot of logic. Some of the things that you learn in logic are, gee, that's nice, but deMorgan's laws are really useful. And remember, from the computing perspective, one of the things that you want to look at is circuit design, which is not part of this course, but this course is supposed to set you up to study that. And deMorgan's laws play a big part in circuit design for making circuits that do interesting and important stuff. deMorgan was kind of an interesting guy. He was born in India and grew up in England and was at the University of Cambridge, and his career was kind of cut short there because he refused to go along with making religious pledges. So there's a freedom of religion question there. And he was more interested in logic. One of the things that he said, which I find very inspiring in two different ways, is that he didn't think that mathematicians did enough logic. That's obvious. Mathematicians need to do logic. But he also didn't think that logicians did enough mathematics, because what ends up happening is logicians who just do logic, some of it's, gosh, that's nice, but it's not useful. But if they were doing mathematics, they would see the back and forth that's useful. Okay, so let's get into the laws themselves. deMorgan's laws have to do with what happens when you negate a compound statement. And actually, all you have to do is negate a thing involving two statements, and then we can chain them all together. And so if we can do two, then we can do those two and a third, or those three and a fourth, and so forth and so on. So there are two main deMorgan laws, and they appear in two places. So this is what? And they're not really explained in a lot of cases. They're just almost taken for granted. So I'm writing them out as I speak. And they have a nice kind of symmetry to them. And on the other hand, they seem to take a fairly large amount of time to write. So let me make sure I'm doing that correctly. So here they are. They appear in two sections in the textbook that we're using. In section 3.4, in that table of logical facts that are useful, many of which aren't really explained all that well. And then they occur again in section 4.2, where there's a table of set theory facts. So later on, we're going to go back and talk about set theory some more. And deMorgan's laws appear in each of those tables. So what's going on with that? Well, we're going to try to get into it. Anyway, here is the logic version. The negation of an and is the or of the negations. The negation of an or is the and of the negations. So there's that nice kind of symmetry about them. And it can actually be hard if you're looking at things in natural language to try to tease out, well, if Sue carries an umbrella and the cat is thirsty, then what is the negation of that? That's not really useful. One of the places where we're going to use this is when we study implication, which is next, and where negation is one of the key things in determining what implication really means. But let's not get too far ahead of ourselves either. So how are we going to establish that deMorgan's laws are true? And I'm going to do it two different ways. One with what we just talked about using truth tables, and the other I want to do using some set theory. So that's looking ahead and looking back. So it's not like too much of a forward reference that the compiler is going to crash, but it is something that will come back later. So with two propositions, we need 4 rows in the truth table, and so I'm going to write them out. I'm going to try to color code them. I'm probably going to get confused about the color coding, but I will do my best. So when the propositions are P and Q, we know to start the truth table with I'm sorry, 1 0 1 0, true false true false. That's for the Q, and for P 1 1 0 0, and so at least I've kept the color coding there. And remember, the textbook writes these the other way. It's still correct. You have to read what it is that you're looking at, but this is the more commonly used way of writing these, although there is a good argument for their way. Okay, so now let's look at P and Q. So I'm going to write the symbol, this V, upside down V. And P and Q is true exactly when both P and Q are true and no place else. So it's like binary multiplication. So 1 0 0 0. So that's P and Q. And what we're interested in, though, is in the negation of P and Q. So I'm just going to do the negation. That's 1/2 of deMorgan laws. The negation of 1 is 0. The negation of 0 is 1. So I'm just going to write them out. 0, 1, 1, 1. So I've got P and Q and the negation of P and Q. And now let's look at the negation of P separately from the negation of Q. We'll just do those individually. So I'm going to do those both at once. P was 1 1 0 0, so the negation is 0 0 1 1. Q was 1 0 1 0, so the negation is 0 1 0 1. And the deMorgan law says that we want to look, I'm sorry, I'm looking at the wrong one. It says that we want to look at the OR of those two. So I'm going to write that out. So that is the negation of P or the negation of Q. And that's true exactly when one or the other or both are true. And so we end up with 0 1 1 1. In the first row, the way I write it, which is the way most people write it, the negation of, sorry, there it is. In the first row, they're both 0, so their union, excuse me, I'm getting ahead of myself. Their OR is 0, but every place else has at least 1 1. So, and if you look, these two have exactly the same values. So this is the funny thing about truth tables, that the truth table is kind of the proof is in the pudding. When you have two variable statements, P and Q, when you look at the truth table, you've looked at every possible value of P and every possible value of Q and every possible combination of those. And so this thing that you're computing, and this is computing, this thing that you're computing, if you compute it one way, you get a certain answer. It's the answer that counts. And if you compute it another way, you get the same answer. So in all possible cases, those two computations provide the same answer. And so what that means is, if you have to do one and it's not really kind of working out the way you like, well, you try doing it the other way. You'll get the same answer, but you'll come about it differently. So these are equivalent. And that's the first of the deMorgan laws. So there they are. There's another way of thinking of deMorgan laws, which is, you have to be a little bit careful to make sure that you're being equivalent, but which is to think of it in terms of sets. And propositions and sets don't really seem to be all that related. A set is, a bunch of ducks floating on a pond, and a proposition is, there are 12 ducks on the pond. That may or may not be true, but it is either true or false. And a set is, hey, there's some ducks on the pond. Okay. Well, let's get our ducks in a row here, and we can make propositions about sets. Now, this isn't what the book talks about as far as sets of propositions, or now I can't remember the exact title that they use. Um, so if we have some sets, we can make propositions about them. And so I'm going to do that. So this is practice with propositions and with sets. So I'm going to make a statement P. First of all, I have to have some sets here. So I have a set A and a set B, and it's just an automatic thing when you're writing out some sets. Hey, let's do a Venn diagram. It might be useful, it might not be useful. Who knows? So I'm going to make the proposition P that some x, I'm not even going to say what x is, so P kind of depends on x, is that x is an element of A. And while I'm here, the negation of P is that x is not an element of A. Now, if I had some honest sets and some honest elements, I could tell you, oh yeah, this x is in that set. 12 is in the set of even numbers, and 13 is in the set of odd numbers, and 12 is not in the set of prime numbers, that kind of thing. So these are pretty common things in looking at some of the more structural parts of mathematics. I'm going to make another statement, logical proposition, Q, which is that x is in B, the other set. And the negation of Q is therefore that x is not in B. So the deMorgan laws will relate the logical combinations of, say, P and Q. If you negate that, that should come out as not P or not Q. But that's now an actual statement about sets rather than being a very abstract thing. And so, so what I'm going to do is translate the statements about sets into logical statements and so forth and so on. So, and then we'll look at the other form of deMorgan's law. So just to kind of combine these, the statement P and Q, that means, remember, P means that x is in A, I guess it's over here, and Q is that x is in B. And if both of those are true, then x is in A and x is in B, and that's the definition of the intersection of A and B. I'm sorry, I wrote P here and I meant x, and so I will x that out and write x. Okay, so P and Q is the statement that x is in the intersection, and P or Q is the statement that x is in the union. And if we wanted to try to clarify those in our mind a little bit, you can't prove anything, but we might like color in some parts of the Venn diagram or something, but that's okay. So the deMorgan law that we just did was with the negation of the and. So let's do the negation of the or. So let's look at the negation of P or Q. Now, in terms of these specific propositions, that means that x is not in A union B. I'm sorry, the negation, right. P or Q is that x is in A union B, so the negation of P or Q is that x is not in A union B. Now, we can think about what that means, but these come out to be pretty simple. So what that means is, if x is not in the union, then x can't be in either one. If x is in one or it's in the other, then it's in their union. So this means that x is not in A. It can't be in A, otherwise it would be in the union. And it also means that x is not in B. It can't be in B because then it would be in the union. And that looks like some logical statements to me. So let's see what we can come up with that. If x is not in A, that's the negation of P. And if x is not in B, that's the negation of Q. So what I've done is taken these definitions of P and not P up here and applied them to this statement about the sets A and B. And, well, and is just and. So I'll put in the caret for and. And what do we have here? What we have here is that the negation of P or Q is the negation of P and the negation of Q, exactly as the De Morgan laws would have it. But we also have with this an application to the sets A and B, and this would be for any sets A and B. That's the remarkable part of it. So let me see if I can kind of color these in. This is always a little dangerous, but if X is not in A union B, oh, I forgot to label them, excuse me. I have a set A and a set B, and they exist in some universe. And if X is not in the union, that's going to be the part that I'm coloring in pink. Just miss everything that is in neither A nor B is pink here. Okay, I'm having too much fun. And the alternative is that X is not in A and that X is not in B. And so if X is not in A, that's going to be, I'm going to use diagonal slashes for that one way. X is not in A. These always kind of mess up your Venn diagrams. So there's X is not in A. And then in blue, I'm not sure, let me show you what I did there. I'm going to do, with the opposite shading, X is not in B. And so that goes do. So the way I've drawn this one, that includes most of A. Okay, well, that's a bloody mess. But, I'm sorry, De Morgan would be very insulted, being British, if I had said that. What we're looking for is the stuff that is not in both. And when I scan this, you can look at it more carefully. But the double diagonal shaded part is exactly the pink shaded part. And so that establishes on this Venn diagram for these particular sets that De Morgan law is true. It is true more generally. You could do that with the truth table or else using some reasoning about sets. But the De Morgan laws are there. When you see them again, which is very soon, it will be in analyzing the logical combiner, the logical operation of implication, which has been confusing people forever, but we'll see what we can do to make it better.